What if I told you that no matter how fast you run, how hard you push, how advanced your spaceship is, you'll never outrun a beam of light? Not because you're too slow, but because the universe itself forbids this. And to keep light speed constant, it bends time. It contracts space. Reality itself warps, just to obey a single cosmic law. This is special relativity. And once you understand it, you'll never look at time or motion the same way again. Relativity sounds complex, but the idea is simple. Relativity is the idea that motion is always relative to something else. Your experience of time, space, and motion depends on how you're moving. Imagine you're on a train. You toss a ball straight up, it lands back in your hand. To you, it went up and down. But to someone watching from outside, the ball followed a curved path through space. Who's right? Both of you. That's relativity. You feel still sitting in a car, but to someone standing on the road, you're zooming by. There's no absolute rest in this universe. Everything is always moving relative to something else. But here's the twist. When light enters the picture, the rules completely change. Einstein developed two relativity theories: general relativity, which explains gravity as the bending of space-time, and special relativity, which focuses on what happens when objects move really, really fast, close to the speed of light. Special relativity doesn't care about gravity. It's all about speed, motion, and how light behaves for different observers. Special relativity starts with just two ideas, two simple rules that shatter everything we thought we knew. The laws of physics are the same for everyone, no matter how fast they're moving, as long as they're not accelerating. The speed of light in a vacuum is always exactly the same for all observers, no matter how fast they're moving. Sounds innocent, right? But wait. If light speed stays fixed for everyone, something else has to give. Let's say someone's walking on top of a bus at 5 kilometers per hour. The bus is moving at 20 kilometers per hour. Someone standing on the road sees them going at 25 kilometers per hour. Simple. The speeds just add. But now imagine instead of a person, it's light being emitted from the front of that moving bus. You'd expect speed of light plus speed of bus equals even faster light, right? Wrong. Both the person on the bus and the person on the ground measure the light speed as exactly 299,792,458 meters per second. No more, no less. That's the weird part, because in classical physics, this makes no sense. So let's bring in a little math to explain how the universe fixes this. You know the formula. Speed equals distance divided by time. Now suppose you are flying through space at 90% the speed of light. You shine a flashlight forward. Common sense says, the beam should leave you at c plus your speed, right? But nope. You still see the light moving away at c. And someone watching from outside? They also measure it moving at c. But that can't happen if both your distances and time stayed the same. So what's the solution? Well, if speed must stay constant at c, then something else has to give. So the universe bends the rules. To preserve light speed, it contracts distance for fast-moving objects and stretches time. This way, both you and the outside observer see light traveling at the same speed, even if your clocks and rulers disagree. This is where special relativity begins to rewrite reality itself. Imagine two twins. One stays on Earth. The other goes on a journey through space at near the speed of light. Years pass for the twin on Earth. But when the space-traveling twin comes back, she's barely aged. Why? Because time literally ticked slower for the twin who was moving so fast. That's time dilation in action. The faster you move, the slower time flows. For you, from the perspective of someone who's not moving with you. But why does time slow down in the first place? Well, remember this equation? Speed equals distance by time? The speed of light must always stay constant. That's the universal rule. So if you're moving super fast and the universe still wants light to move at exactly the same speed relative to you, then something's gotta give. The only option left? Stretch time, shrink space. I know, that sounds like cheating. But hey, the universe makes the rules. We just discover them. Now you might wonder, if the traveling twin comes back, don't they both think the other one should have aged less? Here's the twist. The traveling twin turned around during their trip. That break in motion makes their frame not perfectly symmetric with the one who stayed still. So the twin on Earth really does age more. And it's not just theory. We've flown atomic clocks around the Earth. When they land, they're a few nanoseconds younger than their twins on the ground. Objects moving fast will appear shorter in the direction of motion, but only to an outside observer. Space itself contracts, but only for the observer watching you move. Now let's talk mass. As an object moves faster and faster, especially near light speed, its relativistic mass increases. This doesn't mean it's actually getting heavier in the usual sense, but that it resists acceleration more. It becomes harder to speed it up. The formula looks like this. So as you approach c, the denominator gets close to 0, and your mass shoots up. But the moment you slow back down, you return to your normal rest mass. That's because relativistic mass isn't some extra material stuck to you, it's just a relativistic effect, not permanent. At human speeds like 100 kilometers per hour, these effects exist, but they're so small they're basically unnoticeable. These aren't just sci-fi ideas. GPS satellites have to account for both gravitational and special relativity, or your location would be miles off. Muons, particles from cosmic rays should decay before they reach Earth. But because they're moving near light speed, their time slows down, and they make it. In particle colliders, particles live longer and gain more mass the faster they go, just like Einstein predicted. So, was Newton wrong? Not exactly. Newton wasn't wrong, he was just working in the world of low speeds. When you're moving at 60 kilometers per hour or even 10,000 kilometers per hour, the effects of relativity are too tiny to notice. Light speed is 300 million meters per second, so the distortion is minuscule at our everyday pace. Classical physics is still super useful. Relativity just extends the rules for when things get extreme. At everyday speeds, special relativity is still happening. Just too small to notice. You're aging a little slower in a car than someone standing still. But the difference is nanoseconds. And if you ever could approach the speed of light, you could time travel into the future. You'd experience minutes, while centuries pass outside. Special relativity teaches us something wild. Time, space, and reality are not absolute. They twist, bend, and adjust just to keep one thing sacred: the speed of light. And as strange as that sounds, every experiment agrees. Want to know what happens when gravity joins the picture? When space-time itself bends under mass? Check out our general relativity video next. Until then, stay bright, stay curious, and remember, this is where weird meets science.